In this research, we are proposing a concept for an Earth-based technology demonstration that could become a precursor for future piggyback payloads on interplanetary missions. Continued advances in miniaturization and consumer technology now make it practical to consider centimetre-scale femtoprobes, as shown in Figure 1, equipped with MEMS sensor suites that can be rapidly produced at extremely low cost. In the mission scenario we are proposing, swarms of hundreds of femtoprobes would be contained within satellite carriers in low Earth orbit, either within small satellites like CubeSats or attached onto larger satellite carriers. A carrier would deploy a swarm of probes to deorbit towards remote terrestrial locations, such as onto the polar ice sheets or into mid-ocean weather systems, delivering distributed in situ measurements and augmenting simultaneously sensed remote orbital data. Upon landing, the surviving femtoprobes could form an ad hoc wireless sensor network, relaying data to the deploying orbiter. Crucially, this low-cost, high-risk strategy could provide a means of de-risking future interplanetary applications while delivering enhanced terrestrial science returns in the near term. Environmental data obtained could act as a technology demonstration for future solar system missions, such as to land on Europa's ice shell to search for signs of microbial life, or to Titan for atmospheric science and oceanography. We have performed a sensitivity analysis by modelling the entry, descent and landing of a swarm ejected from a circular polar orbit of 400 km altitude, where the probes are dispersed between 2 to 400 metres per second in all directions below the local horizon of the carrier. As shown in Figure 2, this covers between 100 to 140 degrees of latitude and 2.2 to 6 degrees of longitude across the range of delta V's considered, with the landing latitude ahead of the point of deployment between 45 and 180 degrees. This dispersion could be achieved at any equivalent point on this orbit. From this, we can consider the potential response times for deployment as a function of the number of carriers in orbit, as shown in Figure 3, where we could have continuous global coverage within 2 hours to anywhere on Earth with as few as 30 carriers. Equivalently, due to the rotation of the Earth, anywhere in the globe could be reached within 12 hours with as few as 4 carriers. And this represents both the optimal scenarios in terms of response time and the most economical in terms of the ability to cover the entire globe. Thank you for listening, and I hope you enjoy reading our poster.